Hey everybody, we're at our final installment of the exploratory data analysis, but we are no longer just going to work with one numeric variable. We're going to work with two variables, and we might have two category variables or two numeric variables or one of each. These are all options. Okay. And it turns out that to make this work, we will be using statistical formulas. So I included a link on the notebook to the page in our appendix of the course notes that explains statistical formulas. I'll show you the ones we're using in this video, but if you want more details, you should check that out. Okay, so we are set up. We have the date subset of this data frame, the opt for optimism, perfectionism. All right, so we have three different questions we can look at, and the data is set up for us. Let's go ahead and initialize everything. These are all questions from the personality data set and the subsets that are contained in it. Okay, so our first example is we have two category variables, and I want you to look at this, right? Because the accept date, ACC date, is the variable. And the question that was asked was, at a time in your life when you're not romantically involved with anyone, a person asks you out and you feel this person has a wonderful personality, but you do not find them physically attractive. Do you accept the date? And the responses are yes or no. Okay. So that's pretty clear what the accept the date is, and it's a two level category variable, right? Two levels, yes and no. And so in a category variable, the number of subgroups that we have, those are called levels. Okay. And so the research question is, does the yes-no response to the accept date question vary based upon biological sex? Okay. So with a and you see there in blue at the bottom, with two category variables, we're going to want to try to do two things. We want to do a cross-tabulation, and we're going to do a mosaic plot, which is a visualization of that crosstabs. All right, so let's jump in and do the crosstabs first, and that's just x tabs. Okay, now the statistical formula we're going to use starts with a tilde. Usually I think of the tilde as the equal sign that goes in the middle, y equals x. Here we're starting with a tilde. Why? Because we have a category variable first, and then we're going to have a plus sign, and then we're going to have the other category variable of biological sex. Okay, so we started with a tilde. Why? Well, the plus sign generally tells R that the variable following it is going to be a category or grouping variable. With the tilde beginning the equation, R realizes, oh, both of these are category variables. They'll both have subgroups. Okay? And so what does it do? It takes all the subgroups in one and puts them across the top. Across the top, we see females and males. Down the side, we see no's and yeses, and that is a cross-tabulation. In statistics, traditionally, it's called a two-way table, a contingency table. There are a lot of names for it, but it is a cross-tabulation of two category variables. Now, this formula is useful, and we're going to just copy-paste it. Why? Well, I'll show you. Because the mosaic plot will use the exact same information, right? So mosaic plot, paste, okay? And let's see what happens. Oh, it does work. Again, the mosaic plot, the same statistical formula lets it know, hey, they're grouping variables. And what does it do? It creates a rectangular area that corresponds to the proportions. And so, let's take a look here, right? So in this side, we have the no's, right? You see the N right there. Those are the no responses. We can see the percentage of no's that are from females and the percentage of no's that are from males. And here's the yes part. And we can see the female's proportion of yeses and the male's proportion of yeses. And those rectangular areas correspond to whatever percentage of the total that is. Okay, and you can see that there's a larger percentage of yeses, a larger area of yeses for the females than for the males. It turns out that the areas for the males and females on the nose is about the same, which makes sense when you look at the data, 28 and 28. Now, the percentages aren't identical, but that's why the areas are much closer on the no side than they are on the yes side. Okay, but it's a nice visualization, and when if everything were equal, we'd have a plus sign here, right? If the proportions were equal for males and females and for yeses and for nos, then the boundaries of the mosaic plot would line up at like an intersection, like a four-way intersection, right? This offset here lets us know, oh, there's some kind of difference. And what we might say in statistics is that that's a dependence. All right, but let's just type the analysis real quickly. And we saw this with the cross-tabulations too, but let's see. So a response of yes is more likely for the females than the males. And I'm going to put this percentage-wise, right? It's not the totals, it's the percentage, right? So we're saying there's a higher percentage of females saying yes than there is for males, all right? A response of yes percentage-wise is more likely for the males than, and also just make the note that this is biological sex for the biological females than the biological males. Okay, I think I have everything down there correctly. And then statistically, we would predict a dependence. Let's see, we would predict that the yes-no response to the accept a question is dependent upon biological sex. Okay, so we have a categorical variable analysis tool, right, called chi-squared. And it's called the chi-squared test of independence. Why? Well, if the variables are completely independent, right, they have nothing to do with each other. And when we reject it all, when we have the opposite conclusion, we find that there's a dependence or a connection. Okay, so the connection numerically is a correlation, but the connection, if we have two category variables that are related, is called a dependence. Okay, so this second sentence isn't the most important, but it is correct and will give some preview of coming attractions. Okay. So two numeric variables. I've already said that we want to create a scatter plot. Okay, and I didn't, I said scatter, not scatter plot. Sorry about that. That'll be incorrect in our notebooks, but we can change it really quickly. Okay, and what are we doing? Well, we have the adult playfulness variable and the optimism variable, and we're seeing if they're correlated, if there's any relationship between them. Okay, so what is adult playfulness? Well, these are folks who have childlike qualities to their personality, and they often relate really well to children. These are people who might splash through a puddle after a rainstorm. They might whistle or dance at odd moments or dress up or dress down just for fun. They have some childlike, some playful qualities in their personality. And this was supposed to be a, supposed to be a hyperlink, and the hyperlink did not make it into this version, and I'm sorry. So does the playfulness quality correspond to optimism? What are we going to do? Well, we want to do a scatter plot, but a scatter plot isn't that hard. You just say plot and you tell it the two variables. And this is a more standard statistical formula. So if we say plot, and what are we doing? Well, we're comparing play tilde optimism and the data equals OPT. I believe I've got this right. Yes. Okay, that works. I didn't remember exactly what we had named it, but I guessed correctly. Okay, so there's a scatter plot. I just do plot. The statistical formula is basically y equals x. So we're saying, hey, the y-axis is going to be the playfulness. That's going to be the dependent variable. The independent variable is the data vector optimism. Okay, and is there a linear relationship? I have to admit that cloud of points, data points, is rather mystifying, right? So what are we going to do? To superimpose the line of best fit, we are going to use the linear models function, okay? And we're going to create a model, a linear model. So I'm going to go mod, that's going to be the name of the variable that stores our linear model. The function is LM, okay? And everything is the same here, so I'm going to copy paste. I want a linear model of play versus optimism, okay? And then what I'm going to do is I'm going to do AB line mod. Okay, so the AB line is going to create a line of best fit based on this model. Okay, so the linear model is going to create the linear model for play versus optimism. Then the plot is going to make the scatter plot. Now that the scatter plot is already there, now the AB line function superimposes the line of best fit on the plot that's already there. The order is a little bit important here. Okay, and there we go. We have a line of best fit. I'm going to show you a couple of options that I tend to use. First of all, I do LWD is 3. What is that? That's a level 3 thickness to the line. LWD is line width, or line width dimension. I'm not sure exactly what all the letters stand for in the people who created ours mind, but LWD, line width equals 3. And the other thing I like is I like a different color. And I sometimes use red and I sometimes use blue. You can use green, yellow. You can use whatever you want. Why? I just want it bright and easy to see. Okay, so I increase the line width a little bit. I change the color. Why? Because I want the line of best fit is the most important thing now. And it's going to help us with our analysis. So analysis-wise, the problem is that a perfectly flat line of best fit, if it's perfectly horizontal, there's no connection at all between the variables. So what are we assessing? First, we're assessing, is the slope of the line of best fit significantly different from 0? And the answer would appear to be yes. Yeah, it appears that we have a significantly positive slope. Now, is it a steep slope where it's clearly obvious there's a relationship? No, and that's why the scatter plot is hard to read. That cloud of points may have an upward trend to it, but it's hard to detect with the naked eye. Okay, so what's our analysis? Well, the analysis here is that the two variables appear to be positively correlated. Again, we're going to check for a correlation. That's a statistical test we can run. And why? Because the slope of the line of best fit appears to be significantly different from 0 and positive. Okay, so again, that's significantly different from 0. Is that a judgment call? Yeah, there's a gray area there where it's mostly flat, but a little bit of positive or negative slope. And yes, that's a judgment call. On quizzes or tests, we try to make it clear. This, even while it's probably not a very strong correlation, there does appear to be a little bit of correlation there. All right. So, hey, and we're done. That one's easy. There is this linear model thing going on. Okay, so, and there is a little bit of importance to remembering that order, right? That we're going to make the model, make the scatter plot, and then use AB line to superimpose the line of best fit. All right, so our last example is perfectionism versus preferred seat in class. So the preferred seat in class, the sit class variable is its name. And we just ask people, if you walk into a nearly empty classroom and you can sit wherever you want, do you prefer to sit in the front, middle, or the back? Okay. And perfectionism, we got a score on that. And it makes sense that a more perfectionistic personality, right? They want fewer distractions between them and the board and them and the presenter, right? That makes sense. that's my that's my very ill-trained psychology lesson of the day. I know I don't have any expertise in psychology, but it would seem to me that the perfectionist would prefer to sit closer to the front. If you're sitting further to the back, there's a chance that there can be more distractions between you and the board, or somebody tall sits right in the desk in front of you and you can't see the, critical information on the board. Okay, so what are we going to do? We're going to make side-by-side box plots. And we're going to use a statistical formula to do it, all right? So we're going to do box plots. And what are the variables? Well, the numeric variable goes first, and that's perfectionism. And then a tilde, and then the next one is our grouping variable, which is sit class. And remember, that's a capital C in the middle of sit class. And the data frame that we're using is perf, I think. That will work. We shall see. Box plots is not the function. Box plot. Sorry. Okay, there we go. Oh my. So what a nice output we have here. It's a little big. You can resize your screen and see more. But what's nice is we have, right, a nice legend, so we know front, and that was the highest level of perfectionism. Notice these are medians, right? This is the 5-number summary that the box plot uses. Those are the medians, not the means. And the statistical test would be comparing the means. So, are the means different? Yes. It appears so. It appears that we have higher perfectionism scores for those who like sitting in the front, and the lowest perfectionism scores appear to correspond to those who sit in the back. We will make note that there are some outliers here in the middle, the people who prefer to sit in the middle, so there's a little bit of question mark about how perfect this relationship is, but the analysis is clear, right? That the analysis, there I can spell it, is that higher levels of perfectionism tend, let me just say, let me do it the other way. Students who prefer to sit in the front of the classroom exhibit higher levels of perfectionism. Sorry, I hit Control V. Let me switch this into Markdown, get rid of the codes here, and just move this up where we can see it better. Okay. Okay. Students who prefer to sit in the front of the classroom exhibit higher levels of perfectionism, while students preferring the back of class exhibit lower levels of perfectionism. Students who prefer the middle seats in class tend to have perfectionism levels in between these two groups. But two outliers exist, and which may muddle the comparison. Okay, it's not going to ruin the comparison, right? A couple of outliers, but let's just not say anything too dramatic. Let's not say anything like we already know it. It does appear. I mean, and you can and you can look at this box plot and see what I'm saying. It looks really clear that we have the highest levels of perfectionism in the front, the lowest levels of perfectionism in the back, and the middle is somewhere in between. Okay, that conclusion visually is pretty obvious from the box plot. Are there two outliers? Yeah. So I'm just hedging my bets a little bit. I'm just saying, hey, let's in our analysis admit that there's some outliers that may compromise that conclusion. But visually speaking, the conclusion is clear. Front is the highest, back is the lowest, middle's in between. Bada bing, bada boom, we're done. I will tell you that you'll learn the more statistics and data science that you do, that the visualizations are great and they're exactly what turns out to be the case 99 or 98% of the time. But there are these weird cases in statistics where the visualizations seem to be pointing in a clear direction, but when we run the statistical test, it does not bear that out. Okay, so this exploration is giving us some insights into what's probably true about the data. We're getting clues about what is what is usually or typically going to be true. Are our visualizations 100%? No. I'll just tell you that real data from the real world is real messy, and there can be lots of crazy things that you see. But here again, we have a pretty clear pattern that we're seeing. And I'm not saying that you can't trust the pattern at all. I'm saying that don't be surprised in those, 1 in a million type cases where the pattern is clear visually, but you don't see the same results statistically. Okay? And outliers may be one thing that could cause that. All right, so now we're done with exploratory analysis, and we'll be back with the central limit theorem and sampling next week.